Okay, 3, 2, 1, it's jam.
What's up, science fam? You all know the periodic table, but where did all these elements in the periodic table of elements come from? That's what we're going to talk about in this session. My name is Sir Ramon, and this is Science with Sir Ramon. And we're going to start at the beginning of the universe. So we're going to talk about what's known as element formation, also known as nucleosynthesis. So this is the process by which the elements were formed. So for this session, we're going to talk about the evidence and explanations for the formation of light elements in the Big Bang Theory, give some evidence and the formation of heavier elements during star formation and evolution, and write some nuclear fusion reactions that take place in stars which lead to the formation of new elements. So basically, lots of stuff involving the nucleus, the atomic nucleus. So again, we're starting at the beginning, the Big Bang. The Big Bang was an event that had so much energy that for the first split second, nothing but the simplest particles could exist, because anything that's more complex than those simplest particles would be ripped apart by high energy photons that are just going all over the place in that tiny, tiny, infinitesimal initial singularity. But again, just a review, your simplest particles are the fermions and the bosons. So the fermions are basically the matter and antimatter, while the bosons are force particles. Now, for nucleosynthesis, we're going to focus on the quarks and the photons, because during the cooling phase of the Big Bang, again, when it started expanding to the point where the temperature had a significant decrease, there was the possibility of having the quarks come together to form baryons. So the quarks came together to form baryons, and these baryons include protons and neutrons, the ingredients for your atomic nuclei. So again, during the cooling phase, we got baryons already, but these protons and neutrons, these baryons, won't go together unless there's a particle of high energy that they can emit when they go together, and that's the photon. So again, your photons, symbolized by the gamma symbol, are high energy light transmitting particles which are usually emitted when you have baryons coming together. And that allows us to have the nucleosynthesis during the Big Bang. Now, this is just a series of nuclear chemical reactions. So we're looking at reactions between baryons that form atoms or nuclei. So let's decode this for a while. Let's focus on the first one. So this first one has these terms. First, we have 11p. So this just stands for a proton. So the number on the top left is just the atomic mass, how heavy the thing is, while the number on the bottom left is the number of protons that is in that particle. So a proton literally has a mass of 1 because it's one proton, and has one proton because it's a freaking proton. On the other hand, a neutron is something that has mass but has no charge. It's not a proton, so we have this numerical notation where it has a mass of 1 but 0 protons. So this N stands for a neutron. Now, if you have a neutron and a proton and you shove them together really hard, you get this element, which is hydrogen, an element with one proton, and in this case, it also has a neutron. So if you have one proton and one neutron, your atomic mass should be 2. That's why the top number is 2 and the bottom number is 1. Now, the collision between proton and neutron released a photon that is symbolized by a gamma symbol here. So that's the first nucleosynthesis reaction. A proton and a neutron, put them together, you get a hydrogen atom. Now, if you take that same hydrogen atom and you shove another proton into it, what you get is another helium atom. Now, this helium atom has an atomic mass of 3. Now, this helium-3 is actually unstable, but we'll get to that later on. So notice how the numbers look on the left and the right sides of these reactions. If you look at the top numbers of P and H, we have 1 and 2. If you add them together, you get 3, the same 3 that you get for the top number of helium. If you look at the bottom numbers, which are the numbers of protons involved in this nuclear reaction, we have 1 from the proton here, 1 from the hydrogen here, and if you put them together, you get the 2 protons in this helium atom. In other words, if you check the numbers on the left and right sides of a nuclear reaction, they always add up to the same sum. So the atomic mass should always add up to the same sum, and the number of protons should always add up to the same sum unless something's happening to change these numbers. We'll get to that in a bit. We'll have an example of that later on. But in all 6 of these nuclear reactions, which occurred during the cooling phase of the Big Bang, we can see that all of them preserve the atomic mass and preserve the number of protons. Let's check over here in this 5th equation. We have helium-3 and a hydrogen atom. If you put them together, you should get helium-4, a stable helium atom, and a proton. If we check the numbers, we have 3 plus 2. This is the atomic mass. 3 plus 2, it's 5. If we check the atomic mass on the right side, we have 4 plus 1, it's also 5. Let's check the number of protons. We have 2 plus 1, that's 3. And 2 plus 1 is also equal to 3. And there we have it. If you're given a nuclear reaction problem, again, just remember to check the numbers. The top numbers should all add up to the same sum, and the bottom numbers should all add up to the same sum. And the reason for this is because atomic mass, the top numbers, are always preserved, and the number of protons, the bottom numbers, will always be preserved. Right? So that's Big Bang nucleosynthesis. During the cooling phase of the Big Bang, we have protons and neutrons colliding with each other to form 2 particular elements. Highlighted here, we have hydrogen and helium. So we have hydrogen and helium, but they have different atomic masses. This is because they are different isotopes. It's just different numbers of neutrons, but it's still essentially the same element. So hydrogen and helium became the simplest elements and the first elements in the universe. Since they're the first and simplest, they also became the most abundant elements in the universe. In fact, 73%, approximately 73% of the observable universe is hydrogen, whereas helium accounts for around 25%. So the remaining 2% is all the other elements in the periodic table. All right, so again, observable universe does not include dark matter and stuff like that. So moving on, after the Big Bang, it didn't stop there. We need to see where the heavier elements came from, and these came from stars. Because stars are nuclear fusion reactors. They have so much mass and energy that at their core, they're also fusing nuclei. So different types of stars will fuse in different ways. So young stars in particular will fuse hydrogen into helium. Again, one of the most abundant elements in the universe will be fused into the second most abundant element in the universe. So let's look at the process for that. So first we have the proton-proton chain reaction, which only happens with young average-sized stars, just like the sun. So these are also called main sequence stars. So they undergo a proton-proton chain reaction. So in a nutshell, it's basically adding protons repeatedly onto the same thing. So you have the first step, you add protons. Second step, you add more protons. Third step, more protons. So let's see the nuclear reactions in this chain reaction. So first step, you take one proton, you take another proton, and you shove them together. So 1 plus 1 equals 2. 1 plus 1 should be equal to 2, but wait, what's happening here? So in this first reaction, the number of protons didn't add up to the same number. Why? What happened here? So the explanation is on the right side. So what happened is that one of the protons decided it wanted to be a neutron. So again, in this proton-proton chain reaction, when the two protons collided, one of them changed form into a neutron. And in order to do that, it has to release special particles called a positron, so symbolized by plus E, and a neutrino, symbolized by VE. So we won't get into detail on what those are because that's complicated chemistry and physics. But just know that if the proton wants to change itself, it has to give something up. And it gave up that positron and that neutrino in order to change into a neutron. So essentially, since it became a neutron, we only have one proton in one proton in your resultant atom, and since there's only one proton, your element in the periodic table with one proton is hydrogen. So we form hydrogen 2. So hydrogen 2 over here eventually gets hit by another proton. By the way, hydrogen 2 is also known as deuterium. If you watch a lot of sci-fi films, deuterium is supposedly a fuel source or something of the like, Star Trek. So if you take deuterium or hydrogen 2 and you hit it with another proton, take note that hydrogen with one neutron is essentially just, hydrogen without any neutrons, as in hydrogen, which is just a proton, is basically a proton. So again, hydrogen itself, the normal hydrogen, is essentially a proton with an electron. So if you take the electron away, it's just a proton. Okay. So if you have hydrogen 2 and hydrogen 1 and you shove them together, you get helium 3. So we have helium 3. If we check the numbers, we have 2 plus 1 is 3 for the top numbers, and 1 plus 1 is 2 for the bottom numbers. It checks out. So there's just a release of a photon particle because of the addition of that additional proton to the hydrogen. So again, this orange hydrogen here is also equivalent to a proton. Next, if we take two of these helium 3s and we shove them together in the core of a young average-sized star, we can have helium 4 and the production of 2 protons. So again, what happened here is that the 2 unstable heliums became a stable helium nucleus, and then it also gave out some extra protons. So why are there extra protons? It's because we have to balance out both sides of the equation. So if we look at it here, on the left side, we have the top numbers, 3 plus 3 is 6. We need 6 on the other side, an atomic mass of 6. So this stable helium nucleus has 4, an atomic mass of 4. And the protons each have an atomic mass of 1. So if we have 2 of those, we have a total of 2, an atomic mass of 2 for those 2 protons. So 2 plus 4 is 6, and we have equivalent amounts of atomic mass on both sides of the nuclear reaction. If we check the bottom numbers, we have 2 plus 2 is 4, and in the same way, the 2 of helium is equivalent to 2 times 1, which is 2 plus 2, that's 4. Okay, so again, don't forget the this constant, which is on the left of the protons, is supposed to be multiplied to the smaller numbers on the left of the elemental symbol. This just means there's 2 of this particle. All right, so don't get confused by all these numbers that are there. They all have a purpose. The top one is atomic mass, the bottom one is the number of protons, and big numbers on the side are basically the number of those particles. All right, so again, proton has many aliases, and but they will all have a mass of 1 and a positive charge. So if you see a particle which has a mass of 1 and is positively charged, or basically has these two numbers 1, 1, that's basically a proton. So this process is how small stars make helium out of hydrogen. This is the proton-proton chain reaction. We can see here, it's 2 protons slapped together to make hydrogen. Hydrogen gets slapped with another proton, and that's why it's a proton-proton chain reaction. And we get those protons back when we have the stable helium at the end. So those are for young average-sized stars, but for young large stars, we have a different process called the CNO cycle. This stands for carbon, nitrogen, and oxygen cycle. And the reason for this is because carbon, nitrogen, and oxygen are used as catalysts, and they wingman the whole cycle. So when we say catalysts, that means that they don't get used up by the process. They're just helping out in the process. So it's just like in this picture here, carbon, nitrogen, and oxygen is just helping out the protons to pair up with each other and form helium nuclei. So these are the reactions, at least the first 3 reactions that happen in the CNO cycle. We start with an unstable isotope of nitrogen called nitrogen 13. So nitrogen 13 here has an atomic mass of 13 and 7 protons. 13 minus 7 is 6. That means it has 6 neutrons. Anyway, So what happens to this unstable nitrogen nucleus is that it tries to make itself stable. It decays into carbon-13. So what happened here? So what happened is that one proton, again, decided to become a neutron, releasing a positron in the neutrino. So again, if we have a proton turning into a neutron, the atomic mass should be the same, but the number of protons will become -1 because it switched over to become a neutron. So since it changed the number of protons, the identity of the element changed as well. That's why we have carbon-13 here. Now this yellow carbon-13, if we take it over here to the next reaction, if we add a proton to it, so again, we're adding a proton to it, we get nitrogen-14, which is the more or less stable form of nitrogen. So again, if we look at both sides of the reaction, it should add up. 13 plus 1 is 14. 6 plus 1 is 7. So in this case, it's just adding up normally. Now, if we take that stable nitrogen, nitrogen-14, and we add another proton to it, we get oxygen-15. So again, same as earlier, if we just add the top numbers, we get 15. Add the bottom numbers, we get 8. That's how we get oxygen-15. Now, oxygen-15 is also an unstable isotope of oxygen. So it will decay. It will radioactively decay into something else. So this is just the first 3 reactions. Now we move on to the next 3 reactions. So again, we're starting with oxygen-15, again unstable. So since it's unstable, one of the protons will turn into a neutron. It's trying to stabilize by turning itself into a neutron. So again, it releases another positron and neutrino so that it becomes nitrogen-15, another unstable nitrogen isotope. Now, if that nitrogen-15 gets hit with another proton, so again, nitrogen-15 over here gets hit with another proton, we get oxygen-16, the stable isotope of oxygen. So again, this one is more stable, so it'll stay as it is, except if it gets hit by high energy particles, of which there are a lot of these in the core of a giant star. So we have oxygen-16, the stable oxygen isotope, getting hit by a photon or another similarly high energy particle, which rips it apart into helium, a stable helium isotope, helium-4, and carbon-12. So carbon-12 is the stable isotope of carbon. So one easy way to know if it's a stable isotope is if the bottom number is half of the top number. Okay, so what the heck happened here? Why are there so many steps? The proton-proton chain reaction was simpler. This one has like 6 different reactions, and where did that bring us? It still brought us the same result, a helium. It's basically just shoving protons together to make helium. It's the same process, but in this case, we're having the help of carbon, nitrogen, and oxygen, heavier elements that we find at the core of larger stars. Now, they're called catalysts because at the very end, they are regenerated. So this carbon-12 here, if we add another proton to it, it should turn into this same carbon-13. So again, you get the same heavier elements regenerated in the core of a giant star. So essentially what went in is just protons, and what got cranked out is just helium. Carbon, nitrogen, and oxygen and all of their isotopes were just middlemen. They were just steps in a process. Alright, so again, kind of complicated, but you don't need to memorize these steps. You just need to understand the numbers behind it. For example, if this proton did not have the numbers here, you need to be able to fill in what the numbers are, what the atomic mass of a proton is, and how many protons are in a proton or in a hydrogen atom, and so on. All right, so just understand the concept. No need to memorize all of these reactions. All right, so again, old stars like red giants can run out of hydrogen, and when they do run out of hydrogen, they fuse helium instead. So helium being the next best thing to hydrogen, the next simplest element, they will fuse helium instead in what is called the triple alpha process. So in the triple alpha process, your alpha particles, which are basically helium without the electrons, will get shoved together to form the heavier elements of the periodic table. So just like in this picture over here, the red giant stars basically just shove the alpha particles together. So let's see the actual nuclear reactions. So again, take note that alpha particles, symbolized by the alpha symbol, are just helium minus the electrons. So if you take out the electrons of helium, we get alpha particles. So these alpha particles, again, same numbers as the helium nucleus, because again, it's just helium without the electrons. If you shove them together, you get beryllium, a stable beryllium nucleus. So this stable beryllium nucleus has an atomic mass of 8 and 4 protons, but this beryllium will get shoved with another alpha particle. That's why it's triple alpha, because there's a third alpha particle shoved into the beryllium, giving us carbon-12. And carbon-12 is the same stable isotope that we saw earlier. So this carbon-12 is the next heavy element produced in the triple alpha process. So again, it's triple alpha process because there's one, two, three alpha particles. And if we put them all together, we get C12. Now, if C12 gets hit by another alpha particle, what do you think would happen? This will be one of the questions you will find in your brainstorm activity. So I'll leave that for later. So if we get even older and larger stars, they will fuse even heavier elements. But there is a limit to this nuclear fusion in the cores of stars, and that limit is the element iron. So the element iron is like forms an iron wall for stellar nuclear fusion, for stellar nucleosynthesis. So it's either they run out of that iron or they explode very violently in what is called a supernova. But this supernova has so much energy that it can break this iron wall. So the supernova can result in some of the even heavier elements. So that is the result of what is called the R process, which is just short for rapid neutron capture process. So the concept here is that there's huge numbers of neutrons that bombard each other so hard because of the energy of the supernova that they fuse together. And these neutrons, as we saw that the protons can turn into neutrons, the neutrons can themselves also be converted into protons in a very, very high energy state, just like in a supernova. And this R process accounts for much of the elements heavier than iron, including uranium and other very heavy elements. Now, uranium, being a radioactive element, will decay into some of the lighter elements in between. And thus, we have many of the elements of the periodic table, but not all of them. So some of them were actually artificially created by people and not actually found naturally in the universe. At least so far, we haven't found any examples of it because we haven't found stars that are old enough. So we'll find some examples of that in your brainstorm discussion activity. Basically, in this topic, just remember that we are the products of celestial dust. We are forged from the fires of ancient and massive stars. And that means it's our destiny to shine as well. So don't forget, in this topic we discussed the Big Bang nucleosynthesis, how the Big Bang resulted in hydrogen and helium. We discussed stellar nucleosynthesis, how stars of different types create some of the heavier elements up to iron, and how supernova nucleosynthesis creates the elements heavier than iron. And that's pretty much it. I'll see you guys next time.
Party's over.